Welcome to this class. In this class, we will discuss the different operators that can be used to evaluate the implication, and with that, we will try to evaluate the multiple rules with multiple antecedents that can be used to design the fuzzy logic controller, or I will say, in order to design the fuzzy logic controller, basically I have to form the rules. Once I have been formed the rules, then I would like to know how these rules can be evaluated using implication operators, and there are different implication operators are available in the literature, and we will discuss few of them. Once we will see that, then next we must have to know that once the rules have been evaluated, the output of that rules always will be in fuzzified form. But in order to design the system, that is fuzzy system, basically what I want the output in terms of real value or crisp value. So I should know how that fuzzified value can be converted into defuzzified value or crisp value. So for that I should know the different defuzzification methods. So at the last we will just see some of the very well known defuzzification methods which generally can be used to design the fuzzy logic controller. Okay, so with this, let us start with the thing that called approximate reasoning, and in that we have already seen that how can we do the approximate reasoning, and for that how can we obtain the relation between two events. So that suppose I have this relation and I would like to obtain the relation from rules, and that rule can be formed using implication operator, that is A implies B, and again we know that this R, A implies B, can be done in two ways. One will be A coupled with B, and second will be A entails B. Okay, and we have seen how can we compute that A coupled with B can be computed. One of the method we have seen, basically using minimum operator, and A entails B, how can you calculate? Generally is a complement of A ORing with the second event, that is B. Okay, or it is called max operator. Okay, so we will see how again the different operators instead of minimum for the computation of A coupled with B as and A entails B also. Okay, so before that, first let us see how this approximate reasoning can be done using this implication. So we know that we have defined the rule A implies B, and now suppose if I am saying that rule relation I got like this, or rule I have defined that A implies B, then if there is some change in this event, let's say that change is A dash, then what is the output? I have to compute it, and what I have to do, I should know what will be my B dash. Okay, for what it is, if A I said, then it is B. Now if there is a change in this A, instead of A let it be A dash, then what is its corresponding change in B or B dash that I would like to obtain, and that can be obtained using your compositional operator. And a very well known method, or people are generally using the one compositional rule called max min composition, and from that you can obtain B dash will be equal to A dash composition on the relation matrix, which can be obtained from A implies B. Okay, so this is the way to compute the consequence if I know the antecedent and if I know the relation between this A and B. Okay, so this is called as basically the composition rule of inference. Okay, and if I would like to say it geometrically also, so suppose I have two universe of discourse X and Y, and from that let us say I have obtained some relation matrix between A and B, that is A implies B, and it obtained like this. Suppose this is my relation obtained between A dash and B dash. Now suppose I will change in the event, instead of A, let it happen that it is A dash. So I would like to know what will be its B dash. So in order to do that, what can be done? Select the interval. Yeah, I have selected the interval. Then do the intersection. So for that, what I have to do, I have to do the intersection of this interval on this R which has been obtained. Once the intersection has been obtained, then what, find out the maximum from it, or the projection. And what is the projection? Projection will be this much, that is B dash. So here overall what we are doing, we are first trying to do the, to find out the interval, then take the plane, then with this plane do the intersection, and after that do the projection. Means this is as good as your max min composition. Okay, that is how. Let us see it other way also. Suppose I said the rule that A implies B. So for that, let me have like this, X and Y. Roughly I'm telling, suppose I have this A like this. Okay, if this is my A as a fuzzy set which has been described the event A, and if A, then I have B something like this. Okay, and obviously it has to be normalized. Okay, so this is my B. Now suppose I have done this, if A then B. Now what I would like to do, let me have some change in this A. Instead of A, let me have some A dash as a change. So suppose this A dash as a change is something like this. Then what I have should know, that if this is the kind of antecedent happens, then what is its corresponding consequence. Here antecedent means your inputs, consequence means your outputs. Okay, so what to do, you find out the intersection between this, do the intersection. So I have done the intersection, and from this I will find out what is the maxima. So this is the maxima point, and project on it so that it will be projecting on B dash. And once you select this area under this curve, and this will be your B dash. Okay, so this way you can find out the change in the event once I know the rule. So this will be B dash, which can be find out as A dash composition with relation matrix R. Okay, and this how can you write? A dash and R is your A implies B. Now assume here A, B are all my fuzzy sets. Okay, I can write A bar dash, A bar, B bar also, but for sake of writing I will use A bar or A as interchangeably here. Okay, so this also can be solved using max min, and to do that max min, what is to be done, you take it the max from mu A bar dash intersection with mu A bar intersection with mu B bar. Okay, so again if you solve, you will get it one value that will be like this, A and A bar, that is your intersection, and from that select maximum. Okay, so you will get it one maximum value. Let me represent that W, and then you intersect on mu B bar, which is say B bar, B bar, A bar, A bar dash. Okay, so this way you can find out the B bar dash once you know what is A bar dash and the relation. Okay, now with this let us see some operators, some different operators which can be used to evaluate the implication operator. Okay, because these the different operators can be used to reduce the familiar identity called A implies B. Okay, now let us discuss on the implication operators, different operators for implication operation, that is A coupled with B. Okay, So I already told A implies B can be evaluated using two ways. One will be A coupled V, second will be A entails B. So A coupled with B can be computed using T norm operator, and A entails B generally will be computed using S norm, or called T co-norm. All this has been introduced by the scientist called Jade. Okay, so this is also called as the Jade's arithmetic rule also. Okay, so let us see how differently A coupled with B can be computed instead of minimum also. Okay, so that can be done using T norm. So here we know X implies Y, so I would like to find out what is the truthness between X with Y. So you can compute using first operator called minimum operator, or other one is called Mamdani operator or Mamdani implication operator. Okay, and using Mamdani implication operator can be obtained as A coupled with B, which is as good as the minimum operator, and minimum operator from mu A bar of X with mu B bar of Y. Okay, second operator is the Larson implication. And this is also other way to compute the A coupled with B, and here let me represent RL, which is represented A coupled B, and this way you can compute mu A bar of X multiplied with mu B bar of Y. That is, here what you have done, you have selected the minimum value from these two membership values, whereas in Larson implication what we are doing, we are multiplying the two membership values to get it the resultant. Okay, third is called bounded product implication. And in that let me write BP as a bounded product, and this can be implemented as the ORing between 0 with mu A bar of X plus mu B bar of Y minus 1. Okay, so you have mu A bar of X, mu B bar of X, add it, subtract from 1 and or with 0. Okay, so select maximum. Okay, that's the bounded product implication. Fourth operator is called drastic product implication. And in this you can calculate relation as A coupled with B using mu A bar of X intersection with mu B bar of Y, and that can be written as mu A bar of X. This is drastic bound product. If mu B bar of Y is 1, it is obvious, or if mu A bar of X n, then you can write it as mu B bar of X. Okay, and if mu A bar of X is also not 1, mu B bar of X is also not 1, then it will be simply 0. Okay, so this way there are the different operators, you can use it for the computation of A coupled with B. Again, there are four we will see the different operators for the computation of A entails B using S norm or T co-norm. So first is called Lukashevich and Klein-Danes implication. This has been suggested by the scientist, that's why name is Lukashevich and Klein-Danes implication. and this is simply complement of A ORing with B. So this, how can you write, or how can you append the membership function for this relation? Let me write R L K D. This can be computed using S norm, and for that it will be negation of A with B, or how can we write that? It will be maximum from negation or complement of A with B, which is like this, complement of A with B. Basically this has been suggested by Lukasiewicz and Klein-Dien's implication. Next way to compute this A entails B is using propositional calculus. And this can be PC, or I will write RPC, and let us say R and all these are the membership functions. Okay, here let me represent with mu RPC like this. So for that, the membership function using this propositional can be obtained as the complement of A ORing with A coupled with B. So this is what it is, the maximum and minimum from A and B. So this also can be written as maximum, then complement of A, so it is negation of A, and take it minimum from A and B, so it will be mu A bar of X with mu B bar of Y. Okay, assume A bar, B bar or A, B are all fuzzy sets. Then third way to compute this is extended propositional calculus. Okay, and that let me call EPC, and that also you can calculate using negation of A adding with negation of B and then OR with B. Okay, so this can be written as negation of A bar, B bar with B. Okay, negation of A bar and negation of B bar. Okay, and ORing with B bar. Okay, so it means maximum, this minimum. Okay, so it will be max, take it minimum from this two, so it will be minimum from mu A bar, negation means mu A bar complement of X, mu B bar complement of Y. So once you got it, the minimum value from it, then select the maximum from this and mu B bar of Y. So this is the extended propositional calculus. Then fourth way you can calculate using generalized modus ponens, or called R implication, and for that the the membership function for this can be obtained as supremum for that one value which is C, and that can be obtained using two conditions: mu A bar of X algebraic sum with C, okay, less than or equal to mu B bar of Y, and that C has to be 0 to 1. Okay, And what is this supremum? Supremum is the least upper bound. Okay, basically all these formulas are used to reduce the familiar identity. That's it. This depends on your way which operator you would like to select it. Okay, so according to situation or according to the computational complexity, you can select your own operator. Okay, then let's go further. So for that, what we are basically observing, we are observing the fuzzy implication, how to calculate, that is b bar dash can be computed using a bar dash composition with a bar complement b bar, or in simple way I can write b dash will be equal to a dash composition with a implies b. So here observe that there will be one antecedent, that is a, and there is only one rule. Okay, now let us see how this can be evaluated for if there are multiple rules and multiple antecedent. And for that, scientist called Mamdani has been proposed that. So now let us see the Mamdani models to evaluate this for multiple rules and multiple antecedents. Okay, this was all we seen for only one antecedent and one rule. Okay, so let us divide it into different ways. So first let me have single rule and single antecedent. Okay, so how is a Mamdani model to evaluate this rule? So this is simply, just now we have seen also, that is b bar dash can be implemented using a bar dash composition with a bar implies with b bar as a fuzzy set. So what will be the composition rule? Says that you can obtain the membership function for mu b bar of dash y will be equal to max min on mu a bar dash of x and implication, that is a bar implies by b bar, so that also you can obtain as mu r bar on x and y. And if I'll select, it will be max o for x, I can write mu a bar dash of x minimum, so intersection on mu r bar on x y. Again let me expand this, so it will be max over x mu a bar dash of x and mu a bar of x intersection with mu b bar of y, as it is r, that is mu r of xy can be obtained for a bar coupled with b bar. Okay, now you can see here this is nothing but the intersection, so from that select the minimum value. So let me have the minimum value, some intersection I'll get it, from that again select the maximum from it, so it will be obtained as w1 ending with mu b bar of y. So what is this w1? This also I can write as maximum from the intersection of mu a bar of x with mu a bar dash of x. Okay, do the intersection and select the maximum, so which I'll represent with w1, and then I will have the intersection on mu b bar of y. Okay, so this w1 will be my degree of matching between whom and whom, between a bar and a bar dash. So resulting membership function will be equal to the membership function of this b bar, which will be clipped by this w1. So let us say geometrically how this Mamdani model for single rule with single antecedent. So suppose I have two universe of discourse x and y, and on that let me define one fuzzy set which represents some event. So suppose let me call it as a bar, and I am saying that if there is a bar, then I got it some b bar. Okay, so this is something. Oh, this will be mu, this will be on y. Okay, so this is b bar. Okay, now this rule says if a bar, then I got it b bar. Okay, now if there is a change in this event, instead of a bar, let me have a bar dash, something like this. Okay, this way your event has been changed, this way your variable has been changed, which you are going to control. Okay, because a bar, b bar, all these fuzzy sets, we know all these fuzzy sets represent the variables which I would like to control it. Okay, so now if there is a change in this fuzzy variable like this, now what I would like to find out, I would like to find out what will be the corresponding output, or what will be the corresponding consequence. Okay, so for that, what is the rule? Do it using compositional operation, and for that, what I am supposed to find out, I will find out what is the intersection. Yeah, I got this intersection, and from that select maximum. This is what, oh, suppose something like this I got. Okay, and from select maximum, this value will be my w1, and then do the intersection on b bar. So this b bar has been clipped by this w1. See, this has been clipped. So what will be your resultant output? Resultant output will be b bar dash, and this is what I have to obtain it. Okay, so this way you can evaluate the single rule with single antecedent using Mamdani. Okay, now what if there will be single rule, but if there are multiple antecedents? So if there is a single rule with multiple antecedents. Okay, so let us write one fuzzy rule with two antecedents. So for that I need two facts or two premises. So let me call fact 1. Now given thing is that x is a bar and say y is b bar. This is given. Now I'll form the rule. This is fact 2. Okay, so I'll form the rule that if x is a bar and some value y is b bar, then rule says that z is some c bar. Okay, so now if there is a change in that, so if x is a bar dash and y is b bar dash, then what will be the consequence? Consequence will be z is c bar dash. Okay, so what rule here? Rule says that a bar and b bar then implies c bar. Okay, so how can I form a bar coupled with b bar? This gives me c bar. Okay, so let us expand it. So for that, what will be relation? I got it this. Then I would like to know what is its consequence if there is a change in a bar and b bar. So for that, what will be c bar dash? C bar dash will be if a bar dash and y is b bar dash, and then what will be c bar, that is z. Z is will be c bar dash. So this can be obtained as a bar dash coupled with b bar dash, composition with the rule is a bar dash coupled with b bar dash gives me c bar dash. Understood? So if there are the changes in a bar and b bar as a fuzzy set, what will be its consequence? So if x is a bar dash and y is b bar dash, then what I have to obtain it as z is c bar dash. This is what I would like to do it. Fine. So c bar dash, how can you obtain? Using the compositional operator. There is a change in this antecedents now, a bar dash and b bar dash, and already implication has been obtained using a bar dash coupled with b bar dash implies c bar. Okay. Now let us write using max min composition. So how can you write for max min? Now there are two antecedents, so I have to select max from x and y. So it will be a bar dash coupled with b bar dash, and minimum from this r. And what is that rule? It says that a bar coupled with b bar implies c bar. Okay. So again let us simplify this. Max for x and y, it will be mu a bar dash of x, coupled means it will be minimum, and mu b bar dash of y. Okay, here also let me write this also coupling, so it will be again represented using minimum operator. So it will be mu a bar of x ending with mu b bar of y ending with mu c bar of z. Okay, and combine now. So for that I'll get it one thing, take it maximum from this mu a bar dash of x intersection with mu a bar of x. Okay, one thing, take it intersection from that maximum over y, it will be mu b bar dash of y intersection with mu b bar of y. Okay, and again it is intersection with mu c bar of z. Okay, so I have individually taken x and y's and then done. Okay, so this will give me one thing, that is w1, which will be the degree of matching. This will be giving me w2 as a matching, and again what you do, you clipped it by this w1 intersection with w2 on resultant c bar of z. Okay, so this is also w1 intersection with w2, from that select maximum and minimum, and from that clipped on c bar z fuzzy set. Okay, so w1 is the degree of compatibility between a bar and a bar dash, w2 is the degree of compatibility between b bar and b bar dash, and then clipped on c bar. Okay, geometrically if I would like to say, then how will it be? It will be, now there will be two antecedent, one will be for x, second antecedent will be y with membership function, and what is the output as a consequence? This is z. Okay, now it says that if there is a bar like this, suppose I have drawn, okay, or like this I obtained, and there is b bar. Okay, so if I have a bar and b bar, then its consequence says that I got the output, mind you maximum value is all 1, I got c bar something like this, for example. Okay, now what to do? Now this rule I know it, I have obtained it. Now I have a change in this particular event, so I would like to know what will be its corresponding change in the consequence or in the output. So how is a dash? Suppose my a bar dash is happening like this. Okay, so suppose this is my a bar dash, and now b bar dash is happening like this. Okay, so what is this corresponding change in its consequence? So what is to be done? You do the intersection between a and a dash, find out maximum, do the intersection between b and b bar dash, find out maximum. Okay, so this is my w1, this is my w2, and then what is to be done? Do the intersection on it. Means what? I will select the minimum from it and then clipped on C bar. Okay, this is my C bar, and whatever the cleft region I am getting it, this will be my C bar dash. Okay, so this way you can compute the output, and I observe that here all these are the fudgified values. Okay, next model, let's see what if there will be multiple rules with multiple antecedent. Now all we seen for single rule with multiple antecedent. Now third way, let us form the Mamdani model for multiple rules with multiple antecedent. So to clear this, let me take it the example with two rules with two antecedents. So suppose fact is x is a bar dash and y is b bar dash. Okay, rule 1 says that if x is a1 bar and y is b1 bar, then z is c1 bar. Okay, and again I will form one more rule. It says that if x is a2 bar and y is b2 bar, then z is something like c2 bar. Now what is the fact? X is a bar dash, and if y is b bar dash, then what is the consequence? Consequence will be z is c bar dash. Let me clear here. Here also fact I have written wrongly. Fact is x is a bar dash and y is y bar dash, and rule says that if x is a bar, y is b bar, then z is c bar. So consequent is z is c bar dash. Please correct it. Okay. Yeah. Now let us see first it graphically, then we will analyze it, then we will find out mathematically. Okay. So two rules, okay, and two antecedents. Okay, so I have two antecedents, that is x with membership function, y with some membership function, and what is the output or what is the consequent? Consequent I got as z. Okay, now this is for rule 1. Again I have to form for rule 2. Okay, first let us draw for rule 1. So if x is a1 bar like this, okay, this membership function you can take it anything, maybe your triangular, maybe a trapezoidal. Okay, but for explanation I have taken Gaussian, no issue. You can think the fuzzy set, or you can think the real variable has been converted into fuzzy variable, and that fuzzy variable representation may be any membership function, that may be Gaussian, triangular, or what else. And we have seen the different types of membership function also. Now suppose I got the membership function for this very fuzzy set b bar is like this, then c bar is something like this. Okay, So this is for one rule. If x is a1 bar, y is b1 bar, then I got this is 1. Okay. Say like this. Okay. Now one more rule I have to form. So rule 2 says that if x is a2 bar, like this, one more antecedent, that is y is b2 bar, then its output is c2 bar, this is c1 bar. For that, let me take it like this. What is, suppose I got something like this, which is c2 bar. Now what is the fact? Now let me introduce what if there is a change in a1 as a bar dash, something like this. A bar dash. If there is a change in b bar like this, b bar dash. Okay. And similarly in a2 also, suppose there is a change as a bar dash in rule 2, b bar dash is something like this, suppose b bar dash. Okay, so what is its corresponding consequence? That is z is c bar dash. Okay, so for that, what is to be done? You find out the intersection on a1 bar with a1, find out the intersection between b1 bar with b1 b bar dash, and then this is my w1. Okay, this is my w2, w1, w2, and select the intersection. So if I am doing the intersection on w1, w2, it will be minimum as w2. So by w2 it will clipped. So this is the region obtained from rule 1. Similarly, for the rule 2, do the intersection. This much is the intersection. Say this is w3. This much is intersection for w4, and select the minimum by selecting this w3 and w4. So which value will clipped? It will be clipped by w4. So this will be the resultant on rule 2. Okay, and then do the augmentation of both the rules. So augmentation means it will be the addition, this and this and this or this. Okay, so this, mind, for the if I have the more than one rule, then what will be? There will be the augmentation, or there will be the addition. Okay, so what it will be? It will be like addition from this to this. So from here it will be like this, and maybe suppose this is w2, and assume that w4 is less than w2. So this again you add it here, so it will be like something, say for example like this. Okay, so if you concatenate both the things, this is basically the ORing or concatenation. So this is your resultant C bar dash. Okay, and you remember that this is all the in fudgified form. Okay, and then I have to convert it into crisp value or defudgified value. So next we have to see the different defudgification methods available for it. Okay, before going it into, let me finish it with the mathematical representation of it for the multiple rules with multiple antecedents. So how we have written, C bar dash can be obtained using A bar dash coupled with B bar dash, and then do the composition on two rules. One rule say that A1 bar coupled with B1 bar implies C1 bar, or A2 bar coupled with B2 bar implies C2 bar. Okay, this is the formation of rule for multiple, if there are multiple rules. Okay, and this how can we say, let me call this is R1, this is R2. So you can write this is A bar dash coupled with B bar dash, composition with R1 or with R2, and you can use the distribution property and you can write it as A bar dash B bar dash with maximum composition on R1, or A bar dash cross B bar dash maximum composition with R2, and then I can solve to compute miss C bar of Z, and this will be max min. So max min separately on it, max min separately on it, select maximum from the resultant. Okay, so this how can you write for take maximum mu of xy. Recently we have seen for two antecedent with one rule. Okay, so it will be mu A bar dash of x intersection with mu B bar dash of y. Then R1 is again the intersection on mu A1 bar, mu B1 bar and mu C1 bar. So I will directly write now mu A1 bar of x intersection with mu B1 bar of y intersection with mu C1 bar of z. Then ORing with, again select maximum from xy, mu A bar dash of x intersection with mu B bar dash of y intersection with mu A2 bar of x intersection with mu 2 bar of y intersection with mu C2 bar of z. Okay, and then separate x and y. So you can write as maximum for mu A1 bar of x intersection with mu A1 bar of x, ending maximum for y mu B bar dash of y intersection with mu B bar of y intersection with mu C1 bar of z. Similarly I can write for rule 2 also, maximum from x, all this and this, mu A bar, this is A bar dash of x intersection with mu A2 bar of x intersection maximum for y mu B bar dash of y intersection with mu B2 bar of y, this is 1, and then intersection with mu C2 bar of z. So this is your W1, W2, degree of similarity W3, W4. Okay, so which will be W1 intersection with W2 ORing with W3 intersection with W4, and here also written wrongly, W1 intersection with W2, from that minimum clipped on mu C1 bar of z, or W3 intersection with W4 mu C2 bar of z as an intersection. Okay, so let me call this is W5, this is W6, do it on mu C1 bar or mu C2 bar of z, that is ORing. Okay, so W5 intersection on mu C1 bar of z ORing with W6 intersection on mu C2 bar of z. So this will be the addition of this and this, which will be the resultant membership function for mu c bar z of mu c bar dash of z. Okay, so this way you can evaluate the rule. Now I know the resultant consequence of by changing in the events, and then I observe that all these are in fuzzified form. Now what I have to do, basically if I would like to design the controller in real time, I should know the crisp value or the real value. So how to obtain the crisp value or real value from this fuzzified form, that will be going to see in the next class. Okay, so that is called as defuzzification methods. Okay, so with this I would like to stop here. Next class we will continue with the defuzzification methods and the inference system. Thank you very much.